Okay, so welcome to the physics colloquium today. Our speaker is Cole Miller, professor of astronomy at the University of Maryland. Cole was an undergrad at Hillsdale College in Michigan, where he graduated in 1984, summa cum laude in math and in physics at the ripe old age of 15. Then he came to Caltech for his PhD. And obviously there was sort of the issue that as a graduate student, he was younger than most of the undergrads. But when I arrived the next year as an assistant professor, I was younger than most of the graduate students. So naturally, Cole became my first graduate student. I think probably neither of us was really prepared for the experience, but we survived without permanent damage, so far as I can tell. And Cole got his PhD in 1990 on the structure and opacity of atoms in very strong magnetic fields, the cigar-shaped atoms. Then he went to University of Illinois, Urbana-Champaign as a postdoc with Fred Lamb. And by the way, Fred will be giving the physics colloquium later this year. And Cole worked with Fred on accretion on the magnetic neutron stars. Then in 1993, he moved to University of Chicago to work with Don Lamb, Fred's twin brother. And there Cole was a NASA Compton Fellow and worked on X-ray bursts from neutron stars and theories of the kilohertz quasi-periodic oscillations in neutron stars. In 1999, he joined the faculty at the University of Maryland, where he's been ever since. He's won numerous teaching awards, served as director of the NASA Goddard and University of Maryland Joint Space Institute. So among the many topics of research Cole's worked on, he's been a pioneer of studies of 3- and 4-body mergers of black holes and globular clusters and nuclear star clusters, performing spinning black holes and intermediate mass black holes. And I note that that work was begun 15 years before LIGO found its first, so it's prediction, not post-fiction. He's also studied atmosphere models for cooling neutron stars after the bursts to infer the neutron star radius as a function of mass. But today, Cole will tell us about a different way of measuring the neutron star radius as a function of mass using the NICER satellite, studying rotational modulation of X-rays from spinning neutron stars and their implications for the cold nuclear equation of state. So I noticed that his two recent papers on some of the topics he'll talk about already have over 2,000 citations. So this would be like to have Cole explain it.
Thank you very much, Sterl. It's a pleasure to be back here. I had a lot of great times and learned a lot of physics, although, of course, I'm still in the process of learning, as I hope we all are. So here's my general plan. I'm going to try to explain to you why it is that you should care about neutron stars. This is something I might not have to do if there were an astronomy colloquium, but for physics, I'll try a little bit harder. And then I'll tell you about our results for measuring the radii of neutron stars, and I'll explain why that's actually an important thing to do for these two telephone numbers up here, because in astronomy, we have to name things in ways that are inobvious, otherwise it would be too easy to learn, and the aura of mystery and competence would be gone. Then we are going to continue by talking about a few other possibilities of being able to constrain the properties of the cold, dense matter in neutron star cores and what the implications are. Now, I should mention that in this NICER team, Neutron Star Interior Composition Explorer, that final R is capitalized because this is, of course, NASA. In this mission, there were until very recently 2 teams estimating the radii. I led one. Anna Watts of the University of Amsterdam led the other. I'm going to focus on our results, but you should also read theirs. Now, as Sterl mentioned, when I worked with him, he was the one who introduced me to the wonders of neutron stars. And like anybody, I think my field is self-evidently interesting. But let me nonetheless try to tell you why you physicists should care about neutron stars. And the basic reason for this is that neutron stars are wonderlands of extreme physics. They represent the densest accessible matter in the universe, extraordinarily high magnetic fields, strong gravity, and so on. And that means that by studying neutron stars, not only do we get to learn about the astrophysics, but we also learn about extreme physics. And therefore, even though I have colleagues who have told me that from their standpoint, basically neutron stars are failed black holes, I think that neutron stars are in reality worthy of study on their own. What we're going to focus on in particular here is this giant question mark at the center of this marvelous diagram, which is produced by Professor Donny Paz of UNAM in Mexico City. What is going on in the cores of neutron stars? The thing is that the cores of neutron stars have a physical regime in terms of density, temperature, neutron-proton asymmetry that is not something that can be replicated in terrestrial laboratories, nor is the fundamental theory, quantum chromodynamics, something that can be solved in this regime. So observations are essential. And therefore, we don't know, are these cores primarily made of neutrons, as the name would suggest, with a smattering of protons and electrons and muons? Or are they something more exotic, hyperons or quark matter? Are there phase transitions in the center? So this is the lure that we have for the study of neutron stars in this context. So let's dive into them. Although, to be honest, I must tell you that right now, I'm kind of feeling a little bit of the weight of conscience on me, because it may be that I have slightly misled you. So before we go on, let me make a confession to you. And so the confession is as follows. When we try to convince physicists, or for that matter, funding agencies, that neutron stars and their cores are interesting objects to study, we always focus on the composition. Is it free quark matter? Is it hyperons? Is it whatever? And this is very interesting, of course, to nuclear physicists. However, what we can observe of neutron stars directly is actually almost always dependent, instead of on composition, it is dependent on the equation of state, which in general is pressure as a function of something. And in the case of neutron stars, this can be represented usually as a one-parameter family. The pressure is a function of energy density. An observable, which might actually depend somewhat on the composition directly, is the cooling of neutron stars. Basically, because if you have a neutron star which isn't producing any energy of its own, of course, just cools down from formation, the rate of cooling in certain of its times as it's doing this can be strongly dependent on how rapidly and efficiently it can produce neutrinos. That can depend on the composition, but even that can't point directly and uniquely to a single composition, and it's very difficult to measure at this time. We can also ask, what information can we bring to bear from different aspects of nuclear physics? For example, we can do measurements on nuclei, the actual nuclei of actual atoms that we see. They're not quite in the same realm. You don't have 100-to-1 neutron to proton in any nucleus on Earth, but you can get some information. And there is an extrapolative technique called chiral effective field theory, introduced in this context by Steven Weinberg, which is basically an order counting in momenta that can push up to maybe 1.5, maybe twice the density at the center of large nuclei on Earth. So you can get some way away from what we can measure directly. You might also hope that you would be able to use quantum chromodynamics itself. As you know, QCD has the property of asymptotic freedom. If you go to extremely high density, then matter becomes really simple. And you can kind of walk that back to somewhat lower densities and ask, what is the kind of next order correction? But getting below about 40 times that nuclear saturation density, the errors start becoming very significant. So this is why direct measurements are helpful. There are many types of measurements that we can perform of neutron stars, of course. These are the masses, the tidal deformability, the radii, and one or two other things that I will mention. And from here, we have some recent summaries of how to bring this information together, including from laboratory experiments such as heavy ion collisions. Something to keep in mind here is that astronomy is a look but don't touch science. That means that we can't experiment on most things that are relevant, especially to neutron stars. I will admit this is probably good for humanity as a whole, but it is tough on the theorists who are working on this. So this is the limitation we have. We will begin by thinking about neutron star masses, recalling again that the fundamental thing that we might actually be able to constrain is the equation of state. So pressure as a function of energy density is going to be able to predict a variety of things. For example, the relation between mass and radius for a non-rotating star, which is at equilibrium. And this, therefore, also predicts a maximum mass. When you include general relativity and not just Newtonian hydrostatic equilibrium, you find that instead of being able to simply increase your central density at will and lead to stable stars of ever larger mass, there is a maximum mass. This is one of the characteristics that we can measure. Basically, if we can measure a neutron star of a given mass, then a viable equation of state must be able to accommodate that mass or higher. In this context, measurements using radio arrays are critical because nature has kindly provided us with pulsars. Pulsars are extraordinarily good clocks. They're the best natural clocks in the universe. And by timing them as they are moving around in binaries, we're able to measure properties of the system to very high order. So let's begin with the first type of measurement. And that is the case where you have two neutron stars in a binary around each other, and at least one of them appears to us as a pulsar. These are a theorist's dream. Neutron stars are point masses. There are no complications involved with the structure. They just obey gravity. We understand general relativity very well, and we can measure Newtonian and post-Newtonian quantities. Interestingly, what we find is that when we look at all of the cases in our galaxy where we can measure the masses of the two neutron stars in a double system like this, they're tightly clustered around a mass of about 1.35 times the mass of the sun. Now that is possibly indicative. In fact, 20 plus years ago, there were a number of people who argued that this told us that the maximum mass possible for a neutron star was maybe just a little bit above this, 1.5, 1.6 solar masses. If this were true, it would have remarkable implications. It would suggest that there might be something like a phase transition into an exotic form of matter, which would soften the equation of state, meaning lowering the pressure, lowering the maximum mass, and making them small in terms of the radius. However, again, this is astronomy we're talking about. One way to put this in some context is that based on stellar evolution, we expect that our galaxy contains some few hundred million or a billion neutron stars. Of these, total combined, we have detected something on the order of 3,000 of them. So we're only detecting maybe a part in 100,000 of the neutron stars out there. This is something that bedevils astronomy all the time, selection effects, based on the profound philosophical principle that you can only see what you can see. So in this particular case, not only are you only seeing a few of these, but you're looking at types of systems, two neutron stars in an orbit together, which, if you want to be able to measure things to high precision, have to be close enough that they're spiraling together, and that adds to the information you have. Maybe it's just that there's a narrow set of keyholes through which a system must pass in order to get something like this. And, well, yes. As a matter of fact, we actually know now that there are a few neutron stars which have masses in the 2 solar mass vicinity. So here's the list of them, and this is something which is very important because it tells us that whatever the equation of state is of the dense matter in a neutron star core, it must be able to at least sustain this high a mass. And in particular, it means that at the relevant densities, the pressure cannot be too low. So that is to say, the equation of state cannot be too soft. And as we see with some of the recent work by Karim El-Badri, we may be still in the process of detecting these. The higher the mass, the stronger the constraint. So already using this very rigorous approach, we know something about the properties of the dense matter. Again, not the composition, but we know the equation of state has to be at least somewhat hard. But again, why not push it, right? That's part of being a scientist. You don't stay and you don't say we're done. You get greedy, right? And to quote a 1980s movie called Wall Street, at least in this context, greed is good. You want to be able to see, can you get even heavier things? Now, the usual compromise you have to make is that if you're going to try to be pushing more, you might be in a situation where you're no longer as independent of assumptions. With double neutron stars, of which at least one appears to us as a pulsar, well, in that case, you're set. You understand the fundamental theory, the measurements are straightforward, it's all good. But there's a category of neutron stars which are called black widows or redbacks or spider pulsars, because we love naming things. And these often have best estimate masses that are even significantly higher. 2.4, 2.7 solar masses. But here we have a neutron star with a companion that is a very low mass star or even substellar in mass. So this is not a case where you can just wave off any possible systematics. And what I'm showing here on the right-hand side is we're looking at some spectral fits using a couple of codes. And if you look at this, these are the residuals and there are obvious systematics. But okay, if these are actually the masses, this is very important. It tells us that we have to push even harder to look at higher pressures at the relevant densities. And something relevant for a bit later, this is in mild tension with some of the inferences that have been drawn from what is at this moment the only multi-messenger double neutron star event that has yet been seen in the context of gravitational waves. There is a relatively recent bit of work led by Roger Ramani, another PhD graduate of Caltech, of a particular example of one of these black widows where there don't appear to be the residuals. Maybe that's better. It's about 2.35 plus or minus 0.17 solar masses, more work, etc. But these are things we keep in mind. But I also want to mention that radio timing has not stopped giving us some gifts. As I'm going to argue in a bit, one of the most important quantities that we can measure about neutron stars in order to understand the dense matter in their cores is their radius. Now, there are various things that are related to the radius, and one of those is the moment of inertia. Of all the double neutron star systems that we know, only one was at one time a double pulsar system. Within 5 years, one of the pulsars had its beam processed out of our line of sight, so it's now a single. But this has given us tremendously precise measurements. This is important because, again, due to the spectacular timing capabilities of radio arrays with pulsars, you might be able to see something related to the moment of inertia. Now there's GR involved, but basically moment of inertia is like MR squared, you know, the mass to within a gnat's eyelash. So if you know the moment of inertia and you know M, well, you kind of know R. So it gives you similar info. Now this is something where within a year of the detection of this double pulsar, people were forecasting. So this was detected in 2003. So we're going to test your arithmetic in a second. Within 5 years of that, people thought that they would be able to measure with 10% precision the moment of inertia. Now, your arithmetic quiz, is 2003 plus 5 years equal to today? No, it's in the past. So good things never come easily. And the issue is that the actual effect that would be produced is as follows. You have rotating objects. That's why they're pulsars. One of these two pulsars has a rotation period of 23 milliseconds. It is the shortest period of all the category of double neutron star pairs that we know of. The rotation drags spacetime. It's a general relativistic effect, frame dragging. And this means that it actually affects the orbit of the other one. So that in addition to the classical precession of the pericenter, similar to the precession of the pericenter of Mercury, first explained by general relativity. So that's the main effect. You also have this frame dragging. The problem is that to decouple that frame dragging from the much, much larger classical 1 p.m. or first post-Newtonian order precession, you need to have a better precision in the mass measurements than you do now. Nonetheless, by 2030, it's expected you're going to get something like 11% precision on the radius, sorry, the moment of inertia. You know M perfectly. MR squared is the moment of inertia, so that's a 5% measure of the mass. So we're not there yet, but this is something to look forward to in the future. But in terms of what we have now, the next major bit of measurement, which we have available to us in hand, comes from gravitational waves, which have given us so many gifts, thanks to Caltech and some university at the East that I can't bring to mind at the moment. Now, the issue is that gravitational waves come from mass motions. A changing mass quadrupole, reduced quadrupole, is something you need. So the bulk of the neutron star is involved. Now, in principle, gravitational waves can tell us about cold matter, and by cold I mean less than about 10 to the 9 Kelvin, because that's cold compared to the Fermi temperature of 10 to the 12 Kelvin. Cold neutron stars, before merger, you have two neutron stars spiraling toward each other. They've been hanging out for some millions to billions of years, and they're cold. But when you merge them, or when you cause them to be born in a core collapse supernova, they can be much, much hotter. So this is something that potentially has a tremendous amount of information, but all of it depends on the equation of state. This means that you have consistency checks that you can apply. And in particular, if we think about two neutron stars spiraling toward each other, their mutual gravity will cause a deviation from the natural spherical shape. This takes energy from the orbit. It also, because it distorts the stars themselves, it changes the rate at which gravitational radiation is radiated. And this can lead to a signature. There was, in fact, one event, 1708-17, August 17th of 2017, two neutron stars merged. The entire astronomical universe pointed their telescopes at there, and we got gravitational waves. Now, depending on your assumptions, there was no clear evidence for a tidal deformation, but this does give us at least a rough upper limit and how much it could have been deformed by the gravity, the mutual gravity. And if you translate that somewhat model dependently into a radius upper limit, it's maybe less than 13 or 13 and a half kilometers. So whereas the existence of high mass neutron stars tells us the equation of state cannot be too soft, this tells us the equation of state cannot be too hard. So these are complementary in that sense. And again, Katerina has a nice review from a couple of years ago, thinking about what we might get in the future. Now, let's talk about radii directly. And this is going to relate to the NICER mission that I mentioned. I'm showing you here this figure, which is from a paper in 2010, the first paper revealing the existence of roughly two solar mass neutron stars. Now, what we're seeing here is radius in kilometers. For those of you who are really caring about detail, this is the circumferential radius. This is the gravitational mass in solar masses. And for a given equation of state, which some nuclear theorists might come up with, you can predict the mass radius relation. So the ones that manage to make it above the mass of this pulsar are viable. But what you see is that even those have a very wide range of possible radii. And of course, there are many, many other possible equations of state. So you'd love to be able to measure the radius. The problem, though, is that whereas the mass is comparatively simple to measure, it depends basically on gravity. Radius is a lot tougher. It doesn't have long distance effects, and the fundamental theory involved is more challenging. As an example, we can ask ourselves, how would we be able to measure the radius of a star? The easiest way, of course, is if the star is close enough for its size, like the sun or Betelgeuse, you can actually angularly resolve it, measure the distance, use trigonometry, you're good. But for most stars, you can't. What instead you might have to do is make the assumption that the star emits more or less uniformly, say like a black body, and then you get its distance, its flux, you measure its spectrum. The problem is that if you apply that technique to a neutron star, you get ridiculous answers. 2 kilometer radius, 5 kilometer radius, impossible. Things are a lot more complicated. One of the reasons that you can get such huge systematic error is that unfortunately for us, and unfortunately for my PhD thesis, in fact, it turns out that the atmospheres of neutron stars are composed almost entirely of light elements because they have strong surface gravity and there's a sedimentation of heavy stuff. And that the light stuff, hydrogen or maybe helium, is fully ionized. No lines, no edges, purely continuum. So this is where the NICER mission was coming in with a new approach, which we hoped, and so far seems, to be able to give us reasonably precise answers without the systematic issues. A lot of work that I have done with Fred Lamb, and Sterl mentioned Fred is going to be giving a talk here in some time, next spring, I think, right? So next spring. It turns out that the extra dimension of data applied by NICER is the following. NICER is an X-ray detector, and it is aboard the International Space Station. And for X-rays, you count photons, and it can figure out the arrival time of a given photon to better than 100 nanoseconds. That's extremely short. That means that you're able to figure out the spectrum as a function of rotational phase. rather than simply integrating over the flux and spectra, which is what people had been doing before. And all of our analyses suggest that this is able to eliminate the most problematic systematic errors, by which I mean the thing that would kill you is if you got something that looked like an excellent fit to the data, but it turns out that it's actually very wrong, very many standard deviations off. All the different perturbations we've done, synthetic data, making one assumption to generate the data and another to analyze it, we haven't run into that. I have a graduate student, Isaiah Holt, at the University of Maryland, who is continuing to work on that. Now, by the way, for those of you who want to know how else neutron stars can potentially help you or complicate things, I will mention that there are some models of dark matter suggesting that there could be halos of dark matter around neutron stars. If that's the case, then the way that the photons travel from the neutron star surface to us is altered. So in principle, and if you're an optimist, you can imagine getting signatures of dark matter of a certain type that way. So the nicer idea in brief is as follows. We are thinking about neutron stars that are not actively accreting matter. They are just pulsars, they're hanging out, but the process of producing the pulsations that we see in radio waves and often in other bands, but radio waves in particular, involves the motion of high Lorentz factors, electrons and positrons along magnetic field lines that then hit the surface with, gamma of 10 to the 7, and can deposit the energy in a way that bubbles up as X-rays. So these are thermal X-rays coming from the surface, and we can colloquially call these hot spots. So as these hot spots are moving around, then we're going to see a rotational phase-dependent spectrum. And this is what we are analyzing. And here I'm going to highlight Alex Dittman. Alex actually just defended his thesis and is now at the Institute for Advanced Study. So we're doing work using Bayesian statistics. And with that in mind, I want to kind of back up a little bit. It may be that all of you are enlightened enough that you use Bayesian statistics all the time and are happy and comfortable with that. It did not always happen like that. At the time that I was doing my PhD work and my postdocs, in fact, Bayesian statistics were kind of a running joke in some circles. That is to say that people emphasize the fact that you have to be clear and state a prior. So it sounds like all your results depend on the prior. So the standard joke was that a Bayesian is somebody who believes they're going to see a horse, actually sees the donkey, and concludes they've seen a mule. But, at least from my perspective, things changed when the cosmic microwave background experiments like WMAP and Planck started taking their data, and they use Bayesian statistics all the time. And we know that we all want to follow the cool kids, and the CMB folks are the coolest kids around. So as people started thinking, you know what, maybe we should use Bayesian statistics so we can be in the in crowd. The problem, though, is that Bayesian statistics, using it, as I like to say, is a little bit like acting in a moral fashion, which is to say that it may allow you to be smug and feel superior, but it also takes a lot more effort. And so another important development in somewhere in the order of 2010 is that people developed different techniques for doing sampling, even of multi-parameter models, like the ones that we have, where you can use a couple of different approaches. Basically, you can think about what are called Markov chain Monte Carlo, and you can also use things called nested samplers. Markov chain Monte Carlo, at least natively, are best at parameter estimation. You assume a model, you fit the parameters, you get the posterior. Nested samplers, at least natively, are best at model comparison, estimating the evidence. But as an example of how it matters what you're using, this is something which I'm going to show you kind of a brief little video. And what we're looking at here is on the top, we're looking at the final state of sampling of a particular model, which is fitting nicer data for a particular pulsar. This is the heaviest neutron star with a well-known mass. And this is using the nested sampler multi-nest, but then we put it into a Markov chain Monte Carlo and see how the posterior evolves. You can see this is two-dimensional. Vertical axis is the gravitational mass in solar masses. Horizontal axis, the equatorial circumferential radius in kilometers. So the initial state is at the top, then we let it evolve. So we can see that from what had appeared to be a converged run using this particular code multi-nest, it actually stretches out a lot. So the posterior obtained with that particular nested sampler with these particular precision parameters was actually much narrower than it ends up being after a full sampling. So we're running into this a lot. This is one of the reasons why it's taking a while to come up with what we consider to be reliable answers for some of the more complex data sets that we're analyzing with NICER. But I do recommend that if this is the sort of thing you like to work with, you only work with samples where there's some demonstration that there's been a convergence of the results. So here we have our phone numbers for our two pulsars. For the astronomers among you, you will notice the right ascension and declination. Again, I don't know why we can't rename these things, but I guess if a field is thousands of years old, there's a certain feeling that it's working fine. The first one that we announced, which was in 2019, is an isolated pulsar. Because it's an isolated pulsar, no stellar companion around, it means that we have only our NICER data and possibly other X-ray data available to us. We can possibly get some idea of how far it is and so on. But we found a radius of something on the order of 13 kilometers plus or minus 1 kilometer and a mass of around 1.4 solar masses. This, by the way, represents the first time that it's been possible to get a reliable mass of a neutron star that isn't in a binary. Now, for the next one, this is one of special interest and importance because although the first one has a mass which is sort of close to the canonical 1.4 times the mass of the sun, this second one, J0740, has a mass of about 2.1 times the mass of the sun. That's important because it means the central density is probably approaching the highest it can be in a stable neutron star. It is therefore probing a different density and conceivably even a different state of matter. It could be, for example, that the lighter pulsar has a core even down to the center, which is primarily neutrons with some other particles, but it could be that maybe it's free quarks in the center of the higher mass star. So that's why it's especially important. Now, this one is in a binary. We need to bring together a lot of info because unfortunately, this is also X-ray dim. Remember, these are not accreting neutron stars. They're not bright anyway. And this one is particularly dim, even though particularly important. So this is the information we get. Now, looking at those radii, we find that the update, which was led by Alex Dittman, you have a plus minus 1 sigma range of 11.8 to 15.0 kilometers. For those of you who have studied neutron stars, and particularly for those of you who have looked at the evidence provided by the gravitational wave event, GW 170817, you may be looking at that 15 kilometers and say, dude, that's too large. We agree. But the point here is that what we're doing is when we perform an X-ray analysis, we allow the radius to be anything it needs to be to fit the data. After the fact, when we are combining the information from many different sources, including gravitational waves, that's when those high radii get cut out. I mentioned that we have, at least thus far, found that there is not a significant model dependence of our results, meaning that if you have something that appears to give a pretty good fit, you're going to get answers that are reliable. Well, okay, we don't know, we don't have particular divine insight about the mass and radius of these pulsars, but what we can tell you is that when we do different fits, so this, for example, on the left has a model where there are two oval spots, which can be anywhere and overlap anyway, and the one on the right is where you have three oval spots. They're different, but not by much. So there's a consistency, at least in this case. If we look at the particularly massive pulsar, again, this very dim but very crucial source, we need extra information. We need the information about the mass, the observer inclination to at least the binary orbit, and the distance, which is provided by radio. And we also, as it turns out, need information from another X-ray instrument, the XMM Newton satellite, which is run by the European Space Agency. So here we get something which is basically 13 plus or minus a kilometer or two. Interestingly, these are similar radii, despite the 50% difference in mass. So that tells us that we don't have something we might expect if we were getting very close to the maximum mass, which if we went back and looked at those mass radius curves, from your perspective would be there's a quasi-vertical realm where even increasing mass doesn't change the radius much, and then it will roll over. So maybe we're not so near the rolling over period. How then are we going to manage to go from our measurements of any sort whatsoever to the equation of state? Remember, this was the lure that I tried to bring. We want to know what are the properties of the matter. Well, we can go in one direction. We certainly, if we have the equation of state, we can certainly tell you what the mass or radius are going to be, how they're related to each other. But we want to go backward. So this is how, of course, Bayesian statistics come in. And there are a variety of ways of doing this. Katerina here, for example, has been doing a lot of good work on this. I don't think there's a uniquely best way of doing it, but one thing that has been an interesting contribution of Deborah Moravchik, who is a graduate student at the University of Illinois, is kind of adding by hand certain features in the sound speed versus density, which is sort of like pressure versus density, adding in phase transitions, for example, or spikes, and trying to understand whether there's any evidence for such exotic features. And the answer at the moment is no, it's kind of murky. Either way works. If you put all of this together, what you find is that you are now getting very substantial tightening in our understanding of the equation of state. So here, which is one of the summaries that I'll have for this part of the talk, what we're looking at is pressure versus density. And when we're looking at the pressure versus density, the dotted line here is what we're using as our prior. So at a given density, the lower dotted line is the 5th percentile of the pressure for the prior, and the upper is the 95th percentile. And then the red is what you get when you add in all of the information together. The high masses of some pulsars, the tidal deformability, upper limit, and the measurements with NICER. So you can see that especially in a range of maybe 1.5 to 5 times nuclear density, that there's a tremendous tightening. Now, the exact version of this is going to depend on your framework for extending your equation of state to higher densities than we can do direct measurements. And so there are going to be slight differences, but the net result, regardless, is going to be that you have tremendously increased your understanding of this set of matter. We can look at this in another way, and that is looking at the mass radius curve itself. So instead of thinking about the equation of state, we can say, what do we know about the radius of a neutron star as a function of mass? So here, the pink region is the 5th to 95th percentile radius at a given mass. The blue is 25th to 75th percentile. This is what we started out with. This is what we had before NICER. This is adding one pulsar, adding a second. You can see that it is in fact very substantially tightened. So at least in the work that we have done, we're telling ourselves that we pretty much know the radius of a canonical 1.4 solar mass neutron star to about 5%. But why stick with something like this when you can tap into NASA? So one of the interesting things about NASA is they have people who do graphic design and presentations that can be a lot of fun. And therefore, for a particular press release that we had, they did the following. If you look at this and you know your geography very well, you may recognize that this is the area of Washington, D.C. So the University of Maryland is kind of up here. And the red line, for those of you who may know about it, is the accursed Capital Beltway, which basically is something that goes from being a pretty decent system to an 80-kilometer long parking lot during rush hour. You may also notice that NASA is in the United States because they have miles down here. Very embarrassing. But what we're going to see here is we have the inner circle is the -1 sigma radius of a 1.4 solar mass neutron star, and the outer is the +1 sigma as we improve the information we put in. Theoretical here is what NASA decided to use instead of prior, and then we're going to add stuff. So we began with our theoretical range. Then we add the pre-NICER observations, and then pulsar number 1, and finally pulsar number 2. So this is pretty impressive. Basically, we've got these things which are the size of a city, which can comfortably be at least hundreds or more parsecs away, the ones that we're measuring. Of course, you can have things at the other end of the universe, but hundreds of parsecs away, size of a city, and we're measuring these to a precision of a few football fields. So that's pretty good. This is an indication that collectively, all the people who have put their effort into this, radio timing, gravitational waves, X-ray measurements from NICER, and so on, they've really come together in a fashion that has given us a remarkable insight into a realm, again, we can't explore in laboratories. Again, however, why not be greedy? What are the things that we might imagine doing beyond what we already discussed? I would argue that the constraints that I put in that diagram, where things were shrinking in their uncertainty, are pretty robust. Of course, you always have to worry about systematics a little bit, but I think they're pretty robust. But there are yet more constraints that people have tried to put in. Here, there is greater model dependence, but there's a lot of work going on, and it could be that in some years and with more events, we can do even better. The best known of these, I think, has to do with the double neutron star merger, GW 170817. There's a kilonova, which you probably know about, but basically it's ejection from this double neutron star merger that produces very red emission. And by modeling this, you can get ideas about the speed of the ejecta and how much mass was thrown out. And from the properties of the gravitational waves, you can make arguments about the maximum mass, etc. So that definitely helps. And there have been some good review articles written from here, which have kind of brought a lot of this information together. But I'm going to focus on something else, which is an intriguing prospect, which again, to be clear, I'm not suggesting that we put on the same robust level as the main constraints that I discussed. This is high frequency quasi-periodic oscillations from two Batsy gamma ray bursts. Now, a fair number of you in the audience were probably not even born when these observations were made, but NASA had the great observatories. Hubble is the best known. We also have like Chandra and Spitzer. The gamma ray version was the Compton Gamma Ray Observatory. One of the instruments was Batsy, the Burst and Transient Source Experiment. So how do we get all this? Well, thinking about a merger between two neutron stars, a lot of numerical simulations, including work by Elias and his group, show that when you have a merger, if you don't have an immediate collapse to a black hole, you can have post-merger oscillations as the star is trying to settle in. If it were possible to see gravitational waves from them, this would be tremendously informative about a warm to hot portion of the equation of state. It'd be great if we could see that. Unfortunately, they're weak and high enough frequency that detectors aren't terribly sensitive to them. However, Cecilia Carenci, who will be discussing this in more detail at the TAPER seminar tomorrow, applied the approach that I was saying, which is essentially why not be greedy? Even if the gravitational waves are too weak to detect now, maybe, she said, there could be other signatures of this. For example, it could be that since the merger of two neutron stars is believed to produce at least one category of gamma ray bursts, the so-called short gamma ray bursts, and these are supposed to have high Lorentz factor jets, maybe somehow you can wiggle the jets or you can produce something which is going to modulate the jets in a way that encodes these types of frequencies. So we looked and we found one burst from 1991 and one from 1993. And if you take your power spectrum, you see that there's something at about 2600 hertz and about, in this case, 1100 hertz, here 900. But these are two different bursts that have strong evidence of QPOs, and they fall in pretty much the same frequency range as you would expect from these numerical simulations. So we take a deep breath, we take a stiff drink, and we make the assumption that that's what they are. If we do this, and this is work led by Victor Gedges at the University of Virginia. He's a grad student there. He was an undergraduate who worked with Cecilia at the Federal University of ABC in the São Paulo region of Brazil. And when you put this together with some modeling that has been done, believe it or not, you can actually come up with another constraint of the radius of a 1.4 solar mass, therefore canonical neutron star, on the order of between 12 and 13 kilometers. So it's model dependent, you worry about that, but it's intriguing and it's indicative of another line that could be pursued. And I should also mention, of course, there are other interpretations that Elias and his group have been examining. But I think this is interesting, and I recommend you see Cecilia's talk. To conclude, when we think about the measurements that have been performed using NICER, and our group in particular, we've measured two pulsars, very different masses, very similar radii to within the uncertainties. This tells us things about the properties of high density matter, which we didn't know before. They're telling us that it has to have a somewhat higher pressure at the relevant densities, for example, and we're really honing in on what the sizes of these neutron stars are. Again, these have fundamental implications for nuclear physics. From NICER, we are continuing to work on the data. There are improved data sets. New data are coming in all the time. We can look at new pulsars, and we're going to hope to give you these sorts of bits of information. So overall, prospects are bright. And I'll end with the following thought. When I did my PhD work about the properties of atoms on highly magnetic neutron stars, one of the hopes was that X-ray observations would reveal spectra of lines from these neutron stars, which would be able to, among other things, tell us about their mass, their radius, the equation of state of the high density matter. Nature is not that kind. We have fully ionized atmospheres, no lines. However, I am pleased that I have apparently eaten enough vegetables in my life to live to see a moment where we're starting to become data rich in this field. Thank you very much.
Okay, question. Yeah, Bart.
So let's imagine that somehow, or along the lines of what you're saying, eventually we knew the radius as a function of mass for the neutron stars. Is that enough to know the equation of state? I mean, that's also another one parameter if you view it as pressure versus density.
Yes. So if we had, should I repeat the question? So the question is basically, suppose we could measure the radius as a function of mass, presumably for a set of neutron stars of different masses. Is that enough to know the equation of state? If we're able to measure it over a wide range, then it's enough to get very high precision to the equation of state. Yes, because it is a one parameter family going into a one parameter family. It is not by itself enough to tell us the composition, but basically we throw the composition at a bunch of nuclear physicists, and whoever emerges alive has the best model.
Yes, thank you. How would you, so recent observations, experiments in theory have only increased the tension in the continuous equation of state. So for instance, Jefferson lab measurements of the neutron spin thickness have effectively ruled out, together with Jim Latimer's approximations of neutron theory, most of the equation of state that we can use in supernova data in my context. What are your thoughts on how we can resolve this sharp discrepancy?
Yeah, so the JLab experiments, so there are two neutron skin thickness experiments, as you're aware. So the PREX, which is for lead-208, and the CREX, which is for calcium-48. And those are in tension with each other. Now, what are we going to do about this? Presumably nature has selected something. So I think that basically people who are doing the modeling of the equation of state are going to have to tread very carefully. And people who are providing information like the CREX or PREX people or NICER are going to have to present the information with as many proper descriptions and caveats as possible. In terms of tension, it's not at the level yet where you're going to jump off a bridge. Within the existing uncertainties, there's a relatively wide range of pressures at, say, twice nuclear saturation density, which will work. So it's not at critical level yet, I would say.
Good.
Could you flip back to the QPO measurements? Yeah, that right there. I'm just curious if you could say more about how those spectra are put together.
Yes, so we have, well, we have measurements from BATSI of about, well, we have more than 500 short gamma ray bursts, which come in the BATSI catalog. And they have time tagged event data to 2 microseconds. And these are regularly sampled. And they're regularly sampled, which means that we can get FFTs, which means that every frequency is statistically independent. And that's what we're seeing here. We're seeing a focus on the high frequency level. The different color bands are representative of 1 sigma, 2 sigma, 3 sigma. If you have Poisson noise plus a possible extra contribution of frequency independent and therefore white noise. So when we're doing our model comparison, we're comparing things that have 1 or 2 QPOs versus something that has Poisson plus a possible extra white noise. That's what we're doing in both cases. And there's an extensive work that we do to try to make sure we're not being fooled by the fact that these are fairly short bursts.
Thank you.
Yep.
How many additional sources have enough X-rays, like basically a high enough X-ray power to actually be measurable by NICER, like plausibly?
The next one that we're working on has the phone number of J0437, and it is the highest X-ray flux of its category, meaning a non-accreting, and it is a radio pulsar in the entire set. So you may wonder why we haven't revealed this. The other group did work on this and they did publish something. The answer is it's very complicated data, and we're having to use complex enough models that the sampling is not at the level we're convinced is fully converged yet. So we have that. We also have 3 other pulsars that are much dimmer and are unlikely to add a lot of information, but they are things we're going to publish eventually.
For the hotspot bits, do you take at all into account the presumed geometry implied in the radio pulse?
So do we take into account the geometry from the radio pulse? No, but it's consistent anyway. So we actually, we do this in part because, as you may know, if you look at the models that you have for the radio pulses or gamma ray pulses, then formally they're bad fits to the data. And that doesn't necessarily mean that the best estimate of, let's say, the observer inclination or the magnetic inclination are incorrect, but it does give us a bit of caution.
Are these pulsars deformed due to the rotation?
Well, the pulsars deform due to rotation. Yes, they are oblate. This is actually something we have to take into account. So it's an interesting thing. The oblateness of the star, which means that there's certain lines of sight that are hidden from us that wouldn't be in a spherical star, turns out to be important to model. You might think that frame dragging, which is formally first order in rotation as opposed to the oblateness, which is second order, you might think frame dragging would also have to be taken into account, but it's a much weaker effect as it turns out. So we use something which is originated by Sharon Morsink at the University of Alberta called the oblate Schwarzschild approximation. The star has the right shape, but we trace rays as if they're in the Schwarzschild non-rotating spacetime.
Do this observation give enough information to extract something about the equation of state? I mean, the oblateness.
From the oblateness, no. In fact, one of the things that makes the approximation useful is that there are quasi-universal relations for a star that has a certain mass and a certain radius when non-rotating at a given frequency. So that is something, therefore, that desensitizes us to that direct inference, unfortunately.
Thinking about other signals that we can get from the X-rays, is there anything that can be learned from polarization?
Is there anything to be learned from polarization? Absolutely. If we can, that is something which is going to give us, at a minimum, an extra check on the geometry that we're getting from the spots. So that's something that would be useful to put in.
A question maybe related a little to Katerina. So when I was young, and maybe even when you were young, pulsars had centered dipoles with beautiful little round hotspots that were 180 degrees apart on the surface.
Yes,
And I remember Fred Lamb's exposition before NICER was launched about how trivial it would be that the Newtonian physics, you only see one hotspot, the GR immediately you see two, and so it'll all be very simple. But now the hotspots are not opposite each other, and some of them are very long and moon shaped.
yes,
And of course, there's simulations of computer simulations now of rotate neutron stars with a magnetic axis is off, and they also produce round heated rings and so on. So do you think there's some information, equation of stated rate, but as far as the actual shape of the hot spots, how robust do you think you showed an example where 2 versus 3 didn't change the quite fit of the equation of state, but do you have a sense of how well we might use this to actually constrain the hotspots?
yeah, so that's a reasonable question. Of course, we can also look a little bit more in our local vicinity and see that Uranus and Neptune are not centered dipoles either. So it's one of these deals where, unfortunately, if you look carefully at it, it's more complicated than you'd hope. In terms of the information you can obtain, it turns out that the shape of the hotspot, the location matters. The shape of a hotspot doesn't have a big influence unless this hotspot is large in at least one dimension, so a radian or so. And that's essentially because the local emission from an individual point on the star is very broad, and you also have gravitational light deflection. So if you're talking about small spots,
It's more the question of whether there were big arcs, which seem to be indicated in some of the.
yeah, for that, I don't see any way around it. For the first of the pulsars, the J0030 that we analyzed, both groups independently absolutely got long arcs. You cannot have this with pure circles. So that tells us something. People are talking about quadrodipolar things, and these are all millisecond pulsars, which means that they're the return current is something that is coming in a way that it's not dominated by the very distant dipolar field. There can be lots of multipoles. I think that's probably reliable.